Welcome to my YouTube channel, The Intersection. This video on Turing Machine. Turing Machine is a hypothetical computing approach, very powerful, yet it is very simple. As you can see on this graph that I'm showing here, there is a finite control, like we have seen this before in the other computation models that we looked at in this course. But now we have this tape. This tape is unbounded from the right side. It's bounded, of course, from the left, because the tape head has to start from the most left cell. These are cells. These cells contain the symbols, or the input symbols, and this is the tape head. The tape head can read, write, modify. Well, writing is modifying anyway. So, and then it can move right or left, can move only one cell at a time, as we said. These symbols you see at the end look like a square with the three sides. They're called blank symbols. If I can write blank symbols, and they really tell us the end of the input. So the end of the input, this symbol here, 1. So when it reaches this, when we try to move right, and it sees, the tape head sees the blank, it knows it's the end. So what it does, it will write another cell, blank cell. It'll be like, now instead of 2 blank cells, it will be 3 blank cells, and then moves back to the left, and that's the end of the tape. So now we are at the end of the tape. So what happens? Well, the Turing machine has two states. One, it's called accepted state, and the other called rejected state. Unlike the models we've seen before, so you have Q accepted, or we can say QA, or Q rejected, and we always write it as a QR. Can you have another state? Yeah, you can, but that's not desired. You can have a looping problem, and that you're not gonna get an accepted or rejected state. So the best way to describe what happens is to look at the delta, or the transition function, the delta transition function, and you can see in this example here, and you should know how to read this. The Q here is the current state, and the A is the alphabet on the tape, or in this case maybe 1 or 0 in our example here, and then as you can see, the argument of delta starts with 2 arguments. These are 2 args, and it produces a triplet, 3. And so what is this? This is the state that the head moved into. So from Q7 to what, P in this case. And then this is the gamma. That will be written on the tape, and this is the direction where the tape moved. So in this case, the tape moved to the left. And so if you want to do this in a maybe mathematical notations, we can say delta Q cross gamma, and that will yield a Q cross gamma cross the direction. In this case, left. It can be left or right. In this case, in our case here, is left. So it's important that you should know how to read this. Now you can see that the alphabet is a subset of gamma, but it's not the other way around. So gamma is not a subset of the alphabet. One more thing before I move on with an exercise is that you need to remember if you have blanks, like in this case here, we have these blanks here. They do not belong to sigma, but they belong to gamma. So they belong to gamma, not to sigma. They're not part of the alphabet. It is important to understand the transitions on a finite state diagram, as you can see in example 3.9 in your book. And here's the state diagram for that example. And if you look here, there are the transitions are on the on edges, on these edges here. And so how to read these is important. So let's go, if we look at this transition here, it says if you see a 1 on the input tape, change that 1 or replace that 1 with an X and move to the right. That's what this means. In this case here, if you see a 0 or 1, don't do anything, just move to the right. Or you can say if you see a 0 or 1, write a 0 or 1 and then move to the right. And here in this case, if you see a pound, or if you see this hash symbol, just move to the right. Or you can say if you see this hash symbol, write another right on the top of it, hash symbol, and move to the right. And this here, if you see a 1, then just replace that 1 with an X and move to the left. If you see a 0 or 1, in this case here, write an X and move to the left. It's important that you need to understand how to read those. They're explained in your book. So let's look at an example of a Turing machine. In this example, you are to design a Turing machine that will accept the language a to the power n, b to the power n, where n is greater than or equal 1. A's and B's do not have to be in sequence, but they have to be equal. So if you have an A B, that's accepted. If you have A B B is accepted. If you have B A accepted. And if you have, as long as the number of A's and B's are the same. So any one of these are accepted string for this language. So let's start with, I'm going to start with a blank, and I am going to have an A here, assuming I have an a B here, and maybe another B here, and another A, and another B. So I have three B's and 2 A's, and let's put an A here. So now I have the same number of B's. I have 3 A's and 3 B's. So the Turing machine starts from the leftmost. So here's your finite control, and it's pointing to the leftmost beginning of the tape. So it reads the first is a blank, so it moves right, moves in this direction. It sees an A, it crosses it, or in your book it says maybe replaced with any character, replaced with an X, and then it sees a B right after it moves to the right, and replaced with a Y, and then it sees another B, will replace that B with a Y, and then moves right, sees an A, replace that with an X, and then it sees another B, will replace that with a Y, and then it sees another A, will replace that with an X, and now these are like blanks. It sees this blank, it knows this is the end of the tape, so it moves left, as I said at the beginning of this video. It moves left, and now there is no A, it doesn't see an A, it doesn't do anything to this cell, it goes back all the way to the end, and now we are at an accepting state. So here's a better representation of my drawing, better than my hand drawing. Take a look at it, and again, the string I'm testing is A B B A B A. It can be B A A B A A B A B. And now let me move into the other camera so I can show you how to create the finite state diagram, or the state diagram for this Turing machine. For this exercise, where the number of A's and number of B's has to be equal, but not in sequence. So to do this, let's start with the starting state. That's our starting state. So the first transition is a blank, and upon reading a blank, we will move to the right to state Q1. On a Q1, now we encounter our first input, an A, or we'll either encounter an A or a B, an A or a B. So if we see an A, we'll convert that to an X and move to the right, and we go to a state Q1. If we encounter a B, we will convert that to a Y and move to the right. And that's Q2. So that's the edge of Q1. That's Q. Okay. So now when we see a Q1, if we encounter any matching B's, so we will convert that to a Y and move to the left, and that's a Q4. Similarly, if we add here and we are seeing a match A to this B, because we're converting every B to a Y and then moving to the right. So if we see an A, then we convert that to an X and move to the left. Okay. Now, in the path here, on this path here, if we encounter any Y, we will leave it and move to the right. If we encounter any A's, we leave that and move to the right, because we're still not seeing all the A's. And then if we also encounter an X, we leave that X and move to the right. Now here in the Q4, if we see a blank, we go back to Q1. So if we see a blank, we replace with a blank and then move to the right. Similarly here for the B's, anything in the path here, if we see a Y, we leave that Y and move right. If we see a B, we leave that B and move to the right, because we're looking for the matching A's. In this case here, we're looking for the matching B's. And then if we see an X, we leave it and move to the right. Now, at a Q1, if we encounter an X, we leave it and move to the right. And if we encounter a Y, we leave it and move to the right. Now at the Q1, now what happens, what's the next thing? We're going to go all the way back here, and we depleted all. We know that the number of A's and B's all the same. So now if we see a blank, we go to the stop state or halting state. So that's the accepting state. So Q1, 2, 3, let's see, Q5, accepting state, or QA. That's your accepting state. So that's how to draw the state diagram for this problem.